Hi, everyone. Thanks a lot for coming for today's Learn and Share. We are very happy to have Antonio Sanso from EF talking about Bandersnatch. Antonio has been working on quite a few different things. One paper that I read and really enjoyed, but also dread reading, was about VDF a few years ago. But he has worked on quite a few different things. Today he's going to talk about elliptic curve cryptography, more particularly Bandersnatch, and we'll be able potentially to have an answer whether Bandersnatch is real or not. So thanks a lot, Antonio, for joining us today, and the floor is yours.
Right. Thanks, Rafael. Yeah. So just quickly introduce myself. As Rafael said, I'm Antonio Sanso, colleague working at the as a researcher in the Ethereum Core Foundation team. Yeah, today, do a little correction from what Rafael said. This talk in the paper is about a follow-up of Bandersnatch, and I hope you understand through the talk why. It's specifically this joint work I've done with Youssef El-Husni. They print this online. There's a link there you can follow and see. And yeah, as usual, one sec. As usual, mark like the slides that you requires a bit more attention with the red star. Feel free to interrupt me at any time during the call, during the talk, in case you have questions. I don't mind having questions during. So as everything starts with an elliptic curve. So, or like everything that's related to this starts with an elliptic curve. And yeah, what is an elliptic curve to start with? Well, it's nothing else the locus of a cubic equation where the coefficient a and b are over some field of definition. So it's an algebraic curve, and as we know, it's equipped with some kind of group law. So this, what I'm going to show now, was already known by Diophantus, this famous Greek mathematician. So it really discovered this beautiful group law. So here in the picture we have the elliptic curve defined over plotted over real. But he actually discovered that if you have 2 points that are rational, P and Q, you can actually always find a third point, P plus Q. And how do you do that? Yeah, well, you basically trace a line that intersect the curve in they intersect these 2 points P and Q. Being a third degree equation, this line intersects the curve in the third point R, and you just mirror it, and you have P plus Q. So of course, this is not the normal addition, but it's a special kind of addition law. Yeah, in cryptography, though, we are not using elliptic curve over the real or the rational, but we are more interested about elliptic curve over finite fields. So, and they're a bit more ugly than the previous one. So this is a really toy examples where the elliptic curve is defined over a finite field of size 191. Well, now we have all the ingredients to do our beloved Diffie-Hellman key exchange over this E defined over FQ. How do we do that? So pretty simple. The group elements are the points on the elliptic curve E. The operation is the point addition that I've just shown before. And well, we have an adjoint point at infinity that is acts like identity element. The order of the group is the number of points defined by that you can find using the SEA algorithm that is pretty fast. And well, in order to do the Diffie-Hellman key exchange, you need to believe that the elliptic curve discrete log problem is hard on this group. And that's the way to do Diffie-Hellman. In order to see what we're going to describe in this paper, we need some definitions. So this is the way how you compute the formula to know the number of points over EFQ that you compute using this SEA algorithm. The SEA algorithm, it computes the T in this formula. So the number of points is Q plus 1 minus T, where T is the trace frobenius, so-called. And this trace of Frobenius is bounded by this Hesse-Weil bound and cannot be bigger than 2 square root of q. At the same time, the number of points of the quadratic twist of the curve is q plus 1 plus t. One thing that we're going to use heavily in this talk, and we use heavily in the paper, is this so-called CM equation. A CM equation is an equation of this form where we have an additional parameter d that is called the discriminant of the curve. So what we want to do, what we're interested at, is actually solving this equation over the integer. So finding solution of where q, t, d, and v are integer. This equation are called Diophantine equation. If you want really to do elliptic curve cryptography, then what we need is a curve. Now, how do we find this curve? And we basically have 2 ways to find an elliptic curve that's suitable for cryptography. The first way is like what I call the NIST way. And I call it like this because it's how the NIST found the curve using TLS. So the famous P256 and so on were found using this way. And what they do is nothing else than look for a random curve defined over EFQ, computing the cardinality using this SEA algorithm that we just discussed, and see if the order is suitable. So if it's a prime number or a prime number multiplied a small cofactor. This is a kind of rather slow way to find elliptic curve, but it works pretty well. The second way is what I call here the CM way, and it's using something called CM method that we're gonna see a gist in the next slide. It's really, there's really some deep mathematics behind the CM method, but describing it is at high level is not so complicated. The point here is that, well, this curve comes with some additional properties. For example, they have some computable endomorphism. And well, some people think that they're kind of dangerous to use. But at the end of the day, these curves are pretty, the one used in Ethereum and Bitcoin. For example, SecP256K1 is really the curve used in Bitcoin and Ethereum. Well, is built using CM method. So how does it work, this method? So as said, we want to solve this Diophantine equation. And the way to do it is just like we try different discriminants D until and we apply Kornakias algorithm until we find a solution. So Kornakias gives some really, it's really efficient to find solution for this kind of Diophantine equation. And once we find the solution, this implies that we have HD pairs of such curves that satisfies the equation. I say something that is not important for this talk, but for people that are into number theory, this HD is nothing else that the class number of the imaginary quadratic fields of these discriminants. But if you don't know what it is, forget about it. But the important thing is that once we know the existence of HD pairs of elliptic curves, we can actually find these curves using computing the zero of something called Hilbert class polynomial. All this is kind of seems pretty complex, and from the point of view of mathematics, pretty deep. But doing this with some program like Sage is pretty super simple. Now, some motivation of our talk comes from this dichotomy in this this history about Jab versus Bandersnatch. So if we're interested about elliptic cryptography, one branch of it that is really important is called pairing-based cryptography. This will allow us to do super interesting things like BLS signatures or three-party Diffie-Hellman or IBE, that is identity-based encryption. And in order to do that, we need some more definition and some special curve. But the first definition we're interested at is the embedding degree. And the embedding degree is nothing else than the smallest positive integer k, such that you have an R that divides qk minus 1. And if you find this, k is the embedded degree. At this point, you can take the full torsion of EAR that are nothing else than 2 points that have order R. And you can define pairings where the domain definition are these 2 points, P and Q defined over G1 and G2, that are the groups over elliptic curves, and the codomain is over Fk to the k extension of Fk, where k is the embedding degree. For example, the curve used in Ethereum is the most common curve used in pairing-based cryptography at the moment, is BLS12381, and the 12 in this curve stands for the embedded degree of this curve is 12. So the k of this BLS curve is 12. So if we want to do pairing-based cryptography, we need pairing-friendly curves. So the most famous embedding curves are BLS at the moment. Previously, they were Barreto Naehrig, until a few years ago, even the precompile of Ethereum at the moment has only BN curves. But they were the most efficient one until a few years ago. The reason why they're not used anymore is because people believe there is an attack. Actually, not they believe. There is an attack that doesn't make a BN not having any more 128 bits of security, but the bits of security of Barreto Naehrig curves is about 100. So that's why we migrate as a community to BLS curves. And then there are other curves like ASS in this table, or MNT, BW. What is common about this family of curves is that they are defined using polynomial. So the way do you actually find suitable curves is starting from a CDU, and you have the base field, the scalar field, the rest of Frobenius are defined based on these seeds. So you actually are iterating over seeds until you find some suitable parameters, and then as well some properties that will be interesting for zero knowledge. For example, you want as well that the subgroup order R has high duodicity, that is mathful way to say that R-1 must be divisible by a high power of 2. Another thing that's really interesting for ZK, for parent-friendly curves, is that you want to have a U with a low Hamming weight. That again is a way to say that if you take U at the seed and you put in a binary form, you want to have a lot of 0, and this will have the Miller loops being really efficient. And you have other properties that you want to have in order to have suitable parent-friendly curves for ZK. Now, this opens the door to the next chapter of this presentation. Is that is the main actor of this presentation is like embedded curves. The first time that appeared embedded curves was in this work COCO, that I think is like 2015, something like this. And the reason why they appeared is because if you do pairings, if you do ZK over parent-friendly curves, you have the arithmetic happens over the scalar field of BLS. So it would be actually nice to have a new curve defined over the scalar field of BLS where the arithmetic happens, and you can actually prove things about this new curve on your ZK circuit. And this is brings to the main protagonist of this talk, that is Bandersnatch and Job. And basically, this started 3 years ago when Vitalik and Dankrad were working on the Verkle tree or Verkle tri projects, never understood how to pronounce. And they asked for an efficient curve defined over the scalar field of BLS12381. Well, we already knew that Job existed, but Job was built using the NIST way, and so was using randomly finding curves that they were twisted Edwards over the scalar field of BLS12381. Since Dankrad and Vitalik were asked for efficiency, we thought to with Simon and Zhenfei, we thought to apply CM method to see if we had some suitable curves. And the reason why we actually were interested about the CM curves is because they come with the so-called GLB endomorphism that brings some speeds. Indeed, if you see Bandersnatch for not fixed base scalar multiplication, you see that it's actually 42% faster than Job. So we were looking for this curve using CM method, as we said, in order to find CM suitable curves, you actually iterate through the discriminants. So we try discriminant -3, -4. And well, when we arrived to the discriminant -8, we could not believe our eyes, and we found suitable curves. It's Bandersnatch that has is a perfect Montgomery curves being with a cofactor of 4. And as I will mention in the next slides, you want as well to have a twisted curve that is safe. So it's a remarkable fact that as well the twist of Bandersnatch has really high level of security. Now, if you want to really understand why GLV is actually fast, here is a gist of why this is actually fast. So, for example, suppose you want to compute scalar multiplication x times g, where x is a scalar 256 bits, and g is the base, the generator. And these curves that are built using CM method, they come with a fast to compute endomorphism. So suppose that you have this endomorphism phi that allows to compute some other point A, some other point H that is A times G. So at this point, you can do some lattice technique to split the 256 scalar field is a scalar to two scalars of 128 bits. This is a really simple 2x2 lattice problem, so it takes really a few milliseconds. At this point, your scalar multiplication actually can be split in two simpler 120 bits scalar multiplication, and you can apply some multi-base multiplication that is actually faster. In this case, it's simply a 2MSM. And so we found Bandersnatch that, and this show again the previous slide that sees that you have on the right BLS 281, and on the left the embedded curve is either Jab or Bandersnatch. One little parenthesis: the reason why both Bandersnatch and Jab are Montgomery curves is in the past, when elliptic curve cryptography was kind of invented, the curves were defined over a bias-stress model that are of prime order. The point is that if you see the formulas for point addition bias-stress, they're pretty cumbersome, and they come with a lot of corner cases. So people, notably DJ Bernstein, came with the curve 25519 and showed that the formulas are that you have closed formula and it's only arithmetic. And especially the fact that you have closed formula is pretty friendly to have in a circuit. So that's why both Jab and Bandersnatch were looked to be on the Montgomery form. So this is close the historical background part. If you have any question, it will be a pretty good moment to ask. Otherwise, we go to the subsequent part.
I just have a quick question. You just talked about Weierstrass and Montgomery form. What about the twisted Edward form? Because it's also quite interesting. It's a fewer operation than Montgomery in circuits, and you have a complete addition.
So there is an isomorphism between Montgomery and Edward, twisted Edward forms. So every curve can be represented in a bias-stress model. That is the most generic one. But Montgomery curves, they're pretty specific, and they have a cofactor of at least 4, so they cannot be prime order. And same as twisted Edward. So you have an isomorphism, and you can always switch between Montgomery model and twisted Edwards, but that's not the same for bias-stress model. Only one curve out of 4 can be represented by a Montgomery model, because you need a cofactor of 4.
Thank you.
Does that answer your question?
Yeah. Thank you.
If you have any other question, otherwise I will just go to the next part of the talk. All right. Sorry.
Yeah. I have one other question which I could have asked a bit earlier. So you just talked about 2 different ways to find elliptic curves with pairing friendly elliptic curves. You were talking about the NIST way and the CM ways.
This is about the generic elliptic curve, not pairing friendly.
Oh, sorry, yeah. Is there an advantage to use one over the other?
If you have advantage, so the left, the next way is lower, but the problem is like the right way. Some people think that there are some special properties about CM curves, and indeed they are. The fact that you have this endomorphism, so it's good because having this endomorphism brings speeds.
Yeah.
But from the other hand, people like DJ Barnestan, they are afraid that this more structure that you bring to the curve can be dangerous. But again, like the SEC P256K1 that we use in Ethereum and Bitcoin is actually a CM curve. So it's really a big dichotomy. From one side, you have like no structure and slow. From the other side, you have like a lot of structures that brings speed through this GLB endomorphism. But yeah, we don't know yet. We will never know if this structure brings some security issue.
Yeah. Thanks a lot.
Right. So cool. So here we start with the motivation for the new paper. So as we said before, the curves, the pairing friendly curves, they're built using a CDU. So here I put the CDU of BLS12381. So if you take the CDU, your factoring is equal to minus 1 times 2 times 16, and this too big-ish number. And what happened is like I was observing the table of Bandersnatch, and what I noticed is that, well, the order of two of these curves was had a huge overlap with the seed of the BLS12381. So this was kind of remarkable, and of course could not be a coincidence, and required more investigation. And we actually, in this paper done with Youssef, we found a complete explanation of why this happens, and indeed brings a lot of a framework for generalized curves like Bandersnatch that have a prime order and they have equipped up with this GLB endomorphism. And we'll see how this actually is possible. Before to do that, we need a bit of notation. So we just had the same notation before, so where Q was already the characteristics, but now at the moment we're working with a polynomial. So we have a Q that is defined by a polynomial QU, and the TU is the transport Frobenius, and RU is the subgroup order. For the embedded curve, we have a pedix of E, but since the embedded curve are built using the scalar field of the parameterized curve, you have that RU is equals QE of U. This is like by definition. Now, how this is help us? So what we want to do? We want to solve this again the CMA question, but for embedded curves. So we start from the same equation before, and as you can see, we can substitute QE of U with RU, because again, the scalar field of BLS12381, or scalar field of the parent-friendly curves, is the best field of the embedded curve. And now, how can we solve this for BLS, for example? I'm showing you the solution for BLS, but this will happen the same for BN and the KSS. If you see the RU for BLS is this polynomial. This polynomial is a bit special. It's indeed is called cyclotomic polynomial. But again, it's a mouthful way to say that it's a irreducible polynomial where the root of unity are known. And for example, for BLS12, the RU is nothing else than the 12 cyclotomic polynomial. For BLS24, the R is nothing else than 24 cyclotomic polynomial. How does it help? Let's see. So again, we start from our beloved CMA question, and we know now that RU is a cyclotomic polynomial. Now, by construction, we have a number field K that is a number field over for a BLS is over the kth root of unity quotient by the cyclotomic polynomial. And we have some standard result of theory of cyclotomic fields that we can actually use and leverage pretty well. So we know, for example, that if you have a cyclotomic fields, so if you have that K contains square root of -1 if 4 divides K, and the square root of -2 if 8 divides K, and so on. So how does this help again? So step by step, this again our complex multiplication equation, and let's see the information we discovered in the previous slides. How can help? Well, we know that K form a number of fields, and we know that some fields have some square roots that are contained in the fields. So we can actually rewrite our complex multiplication equation in this way. So we know as well that Ru is 0 in the number field. So we actually are taking our previous equation, mod Ru, and we can rewrite in this way. Then we can apply some other rewriting, and basically we know that -d is a square, and we are actually bringing d from the other side and t from the other side, and we have another polynomial we. Now, the fact that -d is a square, by definition, guarantees a solution. How do we find the solution, though? We apply some really efficient algorithm that is half GCD, and from the fact that the solution is guaranteed in this subfield, we are sure that this half GCD is going to spit as a solution. If we apply this for BLS, here is the solution that we find. And so what you can do now is do whatever you were doing before when you're looking for BLS curve, but you can extend the solution to embedded curve. So in one go, you can find BLS curve and embedded curve only parameterized by the CDU. And in this case, what you're interested are the solutions that are involved. And the reason why we're interested about that is because they are a reducible polynomial, and we leverage the Bunyakovsky conjecture that says that if you have a reducible polynomial, produce infinitely many primes for infinitely many integers. So at this point, you can find BLS curves and embedded curves parameterized by the CDU, where the order of the embedded curves is prime. Now you might ask, why prime at this point? You were saying before the bias stress equations have some clumsy formulas. True, but in the meantime, after the GB introduced the curve 25519, we got a new paper from Renes, Costello, and Batina, and we now have as well complete formulas for prime order elliptic curves. So we can actually come back to what we started from to Weierstrass model with prime order and having complete addition formulas to be built in the circuit without any issues. And on top, we avoid annoyance that we have with the cofactor. I don't know if you remember years ago, for example, the ring signature of Monero had a vulnerability because of this cofactor. Now, another thing that we introduced in the paper, we apply our formulas to find new curves. So we have now a BLS 12380 curve with a prime order embedded curve with the efficient endomorphism, a BLS 24315. And of course, our theory explains now completely the Pluto-Aries cycle found by Dara, I think. And I would like to conclude this presentation with a question for you. If someone in the audience will be able to answer this question I have. So basically, what we found now is this. So we've introduced a new BLS 12380 curve with an embedded curve of prime order. This embedded curve of prime order is a J0 invariant. So it's a J invariant zero curve. So this means that you have a cycle. So you have, starting from a curve that is BLS 12380, you have defined over FQ as order R. You have your embedded curve that is base field R, and that's order P. But at this point, you have another curve defined over P that has order R. So you have the cycle, and you have a chain of BW curve that is the standard chain with the BLS. So what you can actually do now is do some halo supernova shenanigans over these two curves. And then at the end, do some ZK magic over BLS 12380 curve. And my question is this any useful? Can you imagine any scenario where this is useful? And this basically concludes my talk. And I'm curious to know if someone has some idea for this. If not, I'm concluded.
It's a good question. Finding pairing of curves to be able to implement Halo, supernova, and so on has never been easy. So having more options is always good. I worked in the ZKVM team, and we've been thinking of using recursion. So we have had some team members looking at supernova, hypernova, and all the new protocols that have been released for the past year or so. And I think that there could be an interest, but I can't guarantee it. It depends on the curve's parameters, how fast it is, and so on. But
this BLS 12380 is again is a ZK friendly curve, same as the Medal curve. So again, like imagine you have all the power of halo, supernova, hypernova on the right. So what you will have, for example, with pasta curves, but at the end you can actually your arithmetic is ready to go on the BLS 12380 curve.
yeah,
because
I think it would be useful. It's for EF more particularly. We've been waiting for BLS 12 for quite a while, and I think we're going to keep it for quite a while too. So I think this could be quite interesting. Sorry, yeah.
Just like keep in mind, there's no BLS 12381. It's a new curve we defined in the paper.
Oh, sorry, I forgot the last digit. Yeah.
Right. So this will be for some entirely new application where, again, it's a new curve defined. But the characteristic here that is new is the fact that you don't have only BLS curve and embedded curve, but since the embedded curve is a prime order and that has J invariant 0, you can do some halo supernova shenanigan there.
Yeah, I think it would be interesting. I could see people trying to use it. I haven't really heard of it so far, but I'm not talking with the relevant people.
All right. This is new again, like this is new on our. So bring the message along. Maybe someone will actually is looking for this, and here's the solution. And we will have some new results coming soon as well, I guess. So on this like curves connections between others. So it's like we'll have more to come.
That sounds great.
And basically that's it. If you have any question about previous slides, otherwise that's the end.
Yeah, unfortunately, I don't see any questions in the chat. I don't have more questions on my end, but I will be sure to relay your presentation and your questions to the relevant teams in EF. I'm sure that the Hello team would be quite interested in looking more in your paper and may come back to you.
All right.
So if there's no more questions, thanks a lot, Antonio, for joining us today. And thanks a lot, everyone, for joining. And see you next time for the next Learning Share session. Have a good day.
Thank you. Bye-bye.